You are the developer of BioniChaos.com, a website that hosts locally on Flask and Apache within an Ubuntu environment. You specialize in creating interactive biomedical data applications with gamification, aiming to make them accessible to the general public. Got it. Right now, you're developing interactive biomedical data applications, experimenting with EEG data, particularly working with ICA components to extract clear signals. You're also exploring genomics, using libraries like Pandas and BioPython for data manipulation, along with visualizing genomic sequences using D3.js. You're experimenting with simulating CRISPR edits and representing nucleotides with color coding. Let me know if you need specific help on these tasks. Understood. Since ICA and PCA weren't part of your focus, we'll stick to the core of your biomedical applications. You're developing tools that process and visualize data like EEG or ECG, and you're also exploring genomics. If you'd like to dive deeper into a specific area or try out new methods, just let me know. Adding ICA, independent component analysis, and PCA, principal component analysis, to your web application can be done smoothly, especially since both are commonly used in biomedical signal processing, including EEG and ECG data. For ICA, you could use a library like MNE or Sklearn in Python to apply it to EEG data, extracting independent signals from the raw data. PCA, which reduces data dimensionality while preserving important variants, can be integrated using similar tools. Both ICA and PCA are computationally efficient, especially when you have GPU resources like yours. Here's a rough outline to integrate them. 1. Client side. Users could upload raw EEG or ECG data in formats like CSV or EDF. 2. Server side. Use Python to perform ICA or PCA. Libraries like Sklearn handle both easily, and you can process the data quickly with your GPU. 3. Visualization. Once the decomposition or dimensionality reduction is done, you can visualize the independent or principal components in your web app using tools like D3.js, which you're already using for genomic sequences. It wouldn't be too difficult given your current stack. Would you like to focus on one method first, ICA or PCA, or try integrating both at once? Parameter reduction and dimensionality reduction are related but distinct concepts, especially in the context of data processing and analysis. Dimensionality reduction refers to reducing the number of features or variables, also called dimensions, in your data while preserving as much of the original information as possible. This is common in high-dimensional datasets like EEG, genomics, or images. Dimensionality reduction methods like PCA are used to transform the data into a lower dimensional space where fewer variables represent the most important variants in the data. The goal is to simplify the data while retaining the core patterns. Parameter reduction typically refers to reducing the number of parameters in a model. For example, in machine learning, models can have many parameters, like weights in a neural network. Reducing the number of these parameters can make the model simpler and less prone to overfitting. This can be done by regularization techniques or by designing the model with fewer parameters from the start. In short, dimensionality reduction reduces the number of input variables or features. Parameter reduction reduces the number of model parameters. In your biomedical application, dimensionality reduction, like PCA, helps make sense of complex data by reducing the number of features. Parameter reduction would come into play if you were designing machine learning models to analyze that data. Sure. Imagine you have a huge amount of data, like brainwave signals, EEG, or information about genes. This data can have tons of different measurements, like hundreds of different points over time. Working with so much data can get really complicated and confusing. Dimensionality reduction is like taking all those measurements and figuring out which ones are the most important. Instead of looking at everything, you focus on the key parts that give you the most information. It's like summarizing a long book into a few sentences, but still understanding the main ideas. Parameter reduction is more about simplifying how you solve a problem. Think of it like baking a cake. If you can make a delicious cake using just a few ingredients instead of many, it's easier and faster. In this case, the ingredients are the numbers your model or tool needs to learn from data. So, dimensionality reduction helps you focus on the most important data, while parameter reduction helps you build simpler models to understand or predict things from that data. At the college level, let's think of it this way. Dimensionality reduction deals with reducing the number of input features in a dataset, making the data easier to analyze or visualize without losing too much important information. Imagine you have a dataset with hundreds or thousands of features, like EEG signals with many electrodes collecting data at various points. Such high dimensional data can be difficult to work with, both computationally and in terms of gaining insights. Techniques like PCA, principal component analysis, transform the data into a smaller set of new features, called principal components, that still capture the majority of the original variants. It helps us remove redundancy and simplify data representation, making complex, high-dimensional data more understandable. Parameter reduction, on the other hand, relates to simplifying the model that processes or analyzes the data. In machine learning, a model has parameters, like weights in a neural network, that determine how well it can learn from data. More parameters mean a more complex model that can capture more details, but also risks overfitting, especially if the data isn't extensive enough to support such complexity. Parameter reduction involves either modifying the architecture, using fewer layers or neurons, for example, or using regularization techniques to make the model more generalizable and efficient. In summary, dimensionality reduction reduces the number of features or variables to simplify the data itself. Parameter reduction reduces the number of model parameters to make it less complex and more robust. Both approaches aim to make data analysis and modeling more efficient and easier to interpret, but they target different aspects. One targets the data, and the other targets the model. Let's break this down by comparing dimensionality and parameter reduction between EEG data and large language models, LLMs, while discussing how useful the models are and how their performance is tested. EEG data, dimensionality and parameters. EEG signals are recorded from multiple electrodes placed on the scalp. If you're recording with 64 electrodes, each measuring brain activity at thousands of time points per second, you end up with a high-dimensional dataset. For example, a 64-channel EEG recording sampled at 500 Hz for 1 minute results in SHA 64 channels 60 seconds times 500 samples second equals 1.92 million data points. Dimensionality reduction for EEG. Imagine applying PCA to EEG data. The goal is to reduce the number of channels or time points by identifying the most important patterns in the data. If you're working with EEG spectrograms, which turn time series into a frequency representation, each channel's data can be represented as a matrix, which can also be reduced using techniques like PCA or ICA. You might reduce 64 channels to just a few principal components, focusing on those that explain most of the variance in brain activity. Parameter reduction. For EEG models, suppose you're building a neural network to classify EEG signals into different cognitive states. Reducing parameters means simplifying the architecture by having fewer neurons or layers. For example, using fewer hidden layers in a deep learning model can reduce the risk of overfitting when you don't have a lot of training data. The performance would then be tested by accuracy on test data, cross-validation, and sometimes by metrics like confusion matrices for classification. LLMs, large language models, dimensionality and parameters. LLMs process sequences of tokens, words or subwords. The input size depends on how long the text is, and the model's dimensionality often refers to the size of the word embeddings, typically 512 or 124 dimensions for embeddings in models like GPT. Dimensionality reduction for LLMs. LLMs transform input text into high-dimensional embeddings. Dimensionality reduction here might occur in optimizing the embedding space or by using attention mechanisms to focus on key parts of the input. For instance, attention in transformers can be seen as a kind of soft dimensionality reduction, allowing the model to pay attention to important parts of the sequence without processing all parts equally. Parameter reduction for LLMs. LLMs are famous for having an enormous number of parameters. GPT-3, for example, has 175 billion parameters. Reducing parameters in LLMs often involves creating smaller versions, like GPT-2 or distilled models, which perform nearly as well but are computationally cheaper. In training and testing, performance is often measured by perplexity, for predicting the next word, or specific tasks like question answering, using metrics such as accuracy or F1 scores. Comparison. Dimensionality in EEG versus LLMs. EEG data typically has fewer input dimensions than LLMs. In an EEG model, you might deal with hundreds of channels or frequency bands, while in LLMs, you're working with word embeddings that might have thousands of dimensions. In EEG, dimensionality reduction directly impacts how well you can extract meaningful patterns, e.g., brain states. If you reduce too much, you may lose important brainwave signals. In LLMs, reducing dimensions too much could lead to a loss in the richness of language understanding, missing context or relationships between words. Comparison. Parameter reduction in EEG versus LLMs. EEG models often have fewer parameters, especially if you're building a small network or using more traditional machine learning methods like SVMs or decision trees. The trade-off is between complexity and the amount of training data. More parameters mean higher risk of overfitting. Need vast amounts of parameters to capture the intricacies of language. However, like EEG models, having too many parameters without enough training data or computational power can lead to inefficient training or overfitting. To mitigate this, parameter reduction in LLMs typically focuses on creating smaller, more efficient versions without sacrificing too much accuracy. Testing and performance. In both EEG and LLMs, model performance is tested by using unseen data. For EEG models, testing involves using metrics like accuracy, F1 scores, or confusion matrices, often tested on different cognitive tasks or states, e.g. detecting sleep stages, focus, etc. For LLMs, performance is measured on tasks like language comprehension, translation, or specific benchmarks, glue, squad, with metrics like accuracy, F1 scores, and perplexity. Reducing dimensions or parameters in both models can speed up computation, but if reduced too much, you lose important information, resulting in poorer performance on tasks. For EEG, this might mean losing the ability to detect subtle brainwave patterns. For LLMs, it could mean losing the context needed to generate or understand coherent language. In summary, while EEG data reduction focuses on simplifying complex brain signals, from many channels or frequencies, to extract meaningful patterns, LLMs focus on simplifying language representations and reducing the model complexity to handle massive amounts of text data efficiently. Both require careful balance between simplicity and performance to ensure the model remains useful for the intended task. To represent the concepts of dimensionality reduction and parameter reduction in a web application, you could use a combination of interactive visualizations and intuitive user controls. Here's how you might approach this without writing any code. Dimensionality reduction, EEG and LLM. For EEG data, you could present the user with both the raw and reduced data through visualizations. 1. EEG time series data. Display raw multi-channel EEG signals, e.g., 64 channels, as a dynamic graph. Each line represents a channel, and users can scroll through time. 2. Dimensionality reduction. Add an option for users to apply PCA or ICA. After applying one of these methods, display the reduced components, e.g. 3 or 4 principal components. The interface could allow users to toggle between viewing raw data and reduced components. You could use sliders or checkboxes to control how many components are visualized. A separate panel could explain the percentage of variance explained by each principal component. For EEG spectrograms, 1. Present the raw EEG data in the form of frequency spectrograms, 2D heat maps with time on the x-axis and frequency on the y-axis, where color indicates power. 2. After dimensionality reduction, display only the most relevant spectrograms, e.g. fewer frequency bands or reduced channels. Again, use a slider or toggle option to adjust how many dimensions, spectrograms, to display after PCA or ICA. For LLM embeddings, you can simulate dimensionality reduction by visualizing word embeddings. 1. Raw word embeddings. Display a scatter plot where each point represents a word or token in a high-dimensional space. You can reduce the dimensions with PCA or TSNE to make it visible in 2D or 3D. 2. Allow users to select how many dimensions to visualize, e.g. from 300 to 50 dimensions, and dynamically show how the clusters of similar words change. Parameter reduction, EEG and LLM. You could offer controls that simulate the process of reducing model complexity. 1. EEG neural network. Let users adjust the number of layers and neurons in a simple neural network model for EEG classification. You could display a schematic of the network, showing how the complexity changes as they adjust sliders to reduce or increase the number of neurons layers. The impact on accuracy could be visualized as well. When the parameters are too few, the accuracy might drop. Show accuracy charts or confusion matrices to visually represent performance changes. 2. LLM parameter reduction. For LLMs, you can present a simplified neural network representation of the LLM architecture. Sliders could control the number of layers or transformer blocks and the number of attention heads. You could show how performance on tasks, e.g., text prediction or sentence generation, changes as parameters are reduced. Visual feedback, such as showing that too few parameters lead to poor text prediction or generation. Comparative visualizations include comparison panels to visually highlight the differences between EEG and LLM dimensionality parameter reduction. Before-after views show raw data and its reduced version side by side. For EEG, this could be raw signals next to reduced signals, fewer channels or components. For LLMs, show differences in text predictions or embeddings before and after parameter reduction. Accuracy versus simplicity. Graphs include a plot that shows how reducing dimensions or parameters affects model accuracy. This could apply to both EEG models and LLMs. Let users see the trade-off between complexity, number of dimensions or parameters, and performance on test data. User interaction, interactivity. Let users interact with the data and models. They could upload EEG files and visualize the original signals versus reduced signals. Input text into the LLM part of the app and see how text generation changes as parameters are reduced. Compare performance metrics, accuracy, F1 score, as they adjust model complexity through sliders or buttons. This approach offers an intuitive way to engage users, making the complex concepts of dimensionality and parameter reduction clearer through direct interaction and visual feedback. You've been working on developing biomedical applications, and we've talked about ways to add features like reducing data complexity for EEG signals and simplifying models for better performance. You were curious about the difference between simplifying data and simplifying models, so I explained how both can make things more efficient, especially when handling brain signals or text analysis. We discussed how to bring those ideas into your web app without diving into any coding details. For EEG, this means showing users simplified versions of the data and letting them interact with how much information they want to see. For text models, it's about showing how tweaking the model size affects how well it works. We also looked at how both types of data, brain signals and language, can be compared when it comes to making them easier to work with and ensuring the models are still useful. The goal is to make the app intuitive, interactive, and focused on letting users see and adjust how much data or model complexity they're dealing with, while keeping everything smooth and understandable. Here's a full explanation and the necessary prompts to help a new developer generate code for your web application. The goal is to include dimensionality reduction, parameter adjustment, and visualizations for EEG and language models. Web Application Overview. The web application will 1. Allow users to upload EEG data, both time series and spectrograms. 2. Provide an interface to apply dimensionality reduction, like PCA or ICA, on the EEG data. 3. Allow users to input text to see how reducing parameters in language models impacts the output. 4. Visualize the results of both the EEG data reduction and the LLM parameter changes in real time. 5. Include sliders or buttons to adjust dimensions and parameters and show the corresponding effect on performance. What's necessary for the app? To get this working, the developer needs 1. A backend that processes EEG data, PCA, ICA, and text for the language model part. Python is well suited for this, using libraries like scikit-learn for PCA, ICA, and transformers for language models. 2. A front-end that allows users to interact with the data, apply dimensionality parameter reductions, and visualize the output. You'll likely use HTML, CSS, JavaScript with D3.js for the interactive visualizations. 3. A server, Flask or Fast API to handle file uploads, EEG data, and requests between the front-end and back-end. Prompts for code generation. 1. Backend for EEG processing, PCA, IC, plain text. Generate a Python backend using Flask or Fast API that allows users to upload EEG data, CSV format. The backend should include PCA and ICA functionality using the scikit-learn library to reduce the number of dimensions, channels. The reduced data should be sent back to the frontend in JSON format for visualization. Necessary steps. Set up Flask to accept file uploads, CSV files. Use scikit-learn to load the EEG data, apply PCA and ICA, and reduce the number of components. Return the reduced data as JSON for visualization in the front end. Ensure error handling for incorrect file uploads or data format issues. Task 2. Backend for language model parameter reduction. Plain text. Generate. Yes, it's possible to link EEG data to a language model, LLM, in both directions, generating a text explanation from EEG data and creating synthetic EEG waveforms based on a text description. Here's how it could be approached. 1. Converting EEG data to a text explanation. This part would involve training a model or using pre-trained models designed to interpret EEG data. Here's a potential setup. EEG to text. Upload EEG data, and the backend processes it to detect patterns. You could use a combination of signal processing techniques and machine learning models to classify certain brain states, e.g. attention, relaxation, sleep stages. Once the classification is done, an LLM, like GPT, can generate a human-readable explanation based on those EEG-derived classifications. Example, if the EEG shows brainwave activity associated with sleep, the model might generate something like, the patient appears to be in a deep sleep stage with steady delta waves dominating the recording. Necessary steps. Use machine learning models, possibly RNNs, CNNs, or transformer-based models, trained on labeled EEG data to classify brain states. Pass these classifications to an LLM to turn the findings into natural language explanations. 2. Converting text to synthetic EEG data. To generate EEG waveforms based on a textual description, you would need to use or develop a generative model that can create synthetic EEG data from specific brain states or activities described in text. Here's how you might approach it. Text to EEG. Users would input a description of an activity, like the patient is focusing on a task, or the patient is in a relaxed state. Based on this description, the system generates synthetic EEG waveforms that match the expected patterns, e.g. alpha waves for relaxation, beta waves for focus. Example, if the text input says, the patient is meditating, the system could generate synthetic EEG data reflecting dominant alpha waves. Necessary steps. Develop or use a generative model, like GANs or a specialized neural network, that can produce EEG-like signals based on input descriptions. Train the model on pairs of EEG recordings and their textual descriptions, such as mental states or activities. How to integrate both directions. To make this work in a seamless web application, you would EEG to text flow. 1. The user uploads EEG data. 2. The backend processes the EEG using signal classification and sends the results to an LLM to generate a text description. 3. The text description is displayed in the front end. Text to EEG flow. 1. The user inputs a textual description of the patient's state. 2. The backend uses a generative model to create a synthetic EEG that corresponds to the text input. 3. The synthetic EEG is displayed in the front end as a waveform or spectrogram. Requirements for the application. 1. Pre-trained models. For both tasks, you'll need models trained on EEG and text data. For generating text from EEG, models need to classify brain activity states, and for generating EEG from text, you need a generative model capable of producing realistic waveforms. 2. Signal processing. For the EEG side, pre-processing like filtering, artifact removal, and segmentation will be necessary to clean up the raw data. 3. Interactive interface. The front end would allow users to upload EEG data, view the generated text, and alternatively input text to generate synthetic EEG. The visualizations would be handled in real time using D3JS or other visualization tools. Challenges. Data requirements. You'd need a substantial amount of labeled EEG data with corresponding text descriptions to train the models effectively. Generative models for EEG. Generating realistic EEG waveforms from text is complex, as EEG data is high-dimensional and varies significantly based on small changes in brain activity. This project is ambitious but definitely feasible, especially with the right dataset and models. Would you like to explore specific tools or architectures for the generative side of this? For generating EEG data from text and converting EEG data into meaningful text explanations, there are a few important tools and architectures to consider. Tools for EEG to text, interpreting EEG. 1. EEG signal processing libraries. MNE Python. This library is excellent for pre-processing, analyzing, and visualizing EEG data. You can use it for filtering, epoching, and transforming raw EEG signals into features that can be used for classification. SciPy NumPy. These can handle basic signal processing tasks, like removing noise and extracting frequency bands, delta, theta, alpha, beta. 2. Deep learning models. Convolutional neural networks, CNNs. CNNs are commonly used for image data, but can also be effective for time series data like EEG. The idea is to apply filters to EEG signals or spectrograms and classify them into brain states, e.g. focus, relaxation. Recurrent neural networks, RNN, or LSTMs. These models work well for time series data because they can capture temporal dependencies. In EEG, they can track brainwave changes over time, leading to better classification. Transformers for EEG. Recently, transformer models, such as EEG-T, have shown promise in EEG signal classification due to their ability to capture long-term dependencies better than RNNs. Pre-trained models. Some research explores pre-trained models on EEG data, similar to how language models work for text. You could fine-tune these models for your specific task, e.g., detecting cognitive states from EEG. 3. LLM for text generation. Use an LLM like GPT-3, GPT-4, or T5 to generate natural language explanations from EEG classifications. For instance, once the EEG model classifies attention, the LLM could generate a detailed explanation, like the patient is exhibiting signs of focused attention as indicated by increased beta wave activity. 4. Implementation, pipeline. EEG, pre-processing, feature extraction, model classification, CNN, LSTM, transformer, text generation, LLM. Hash tools for text to EEG, generating synthetic EEG. 1. Generative models, generative adversarial networks, GANs. GANs are known for generating realistic data. For EEG, you could train a GAN to generate synthetic EEG waveforms based on input conditions, like specific mental states or activities described in text. Conditional GANs, CGANs. This variant of GANs can be conditioned on input. In this case, the text describing the patient's state. You'd input the text, the patient is relaxed, and generate corresponding EEG signals, dominant alpha waves. Variational autoencoders. VAEs are another generative model that can learn to produce data similar to a given dataset. For EEG, a VAE could generate waveforms based on a latent representation of different brain states. Neural ODEs, ordinary differential equations. These can model the dynamics of brain activity over time, offering another approach for generating synthetic EEG from a time-dependent perspective. 2. Text embedding to EEG mapping. Text embedding models. You can use models like BERT or GPT to transform text into embeddings. These embeddings could be input to the generative model, like a GAN or VAE, to produce synthetic EEG. The text embeddings would represent concepts like focus or relaxation, and the generative model would create EEG signals associated with these states. 3. Training the generative model. Dataset. You'll need a dataset that contains pairs of EEG recordings and textual descriptions of the brain state or task the subject was performing. This is necessary for training the generative model. Loss function. Ensure the generated EEG is realistic by using loss functions that measure the difference between the generated EEG and real EEG signals in terms of both waveform similarity and spectral content. 4. Implementation. Pipeline. Text embedding via BERT GPT, generative model, GAN or VAE, synthetic EEG generation, visualization. Steps to proceed. 1. Start with EEG classification. Pre-process EEG data with libraries like MNE. Use CNNs or LSTMs to classify different brain states. Use an LLM to generate text from the classification. 2. Explore generative models for EEG. Begin by generating synthetic EEG using a GAN or VAE trained on existing EEG data. Condition the generation on textual inputs, e.g., using C-GANs or embedding models. 3. Testing and evaluation. Test the generated text from EEG for accuracy and coherence. Test the synthetic EEG from text for realism by comparing it with real EEG data and ensuring it matches the expected brain states. This combination of processing, classification, generation, and transformation links EEG and language models in an innovative way, allowing text and EEG to speak to each other. Certainly. Here are some questions that a PhD candidate conducting research in this area might ask to dive deeper into the methodology, feasibility, and potential challenges of linking EEG data with language models. Regarding EEG to text generation. 1. What specific types of EEG data are most suitable for generating meaningful text descriptions? For example, do we need to focus on task-based EEG, e.g. during cognitive tasks, or resting state EEG to produce interpretable and generalizable results? 2. How would we handle the variability between individual EEG recordings when generating text? Given that EEG signals can vary widely between subjects, how would this affect the reliability and consistency of the text explanations produced by the model? 3. Have there been any studies that successfully combine machine learning with natural language processing to interpret biomedical signals in real time? If so, what methods did they use to ensure accuracy and interpretability? 4. Given the limitations of current LLMs, how would we ensure that the generated text from EEG remains scientifically accurate and not overly generalized? For example, would a fine-tuned version of an LLM be sufficient, or would we need domain-specific models trained on medical or neuroscience data? 5. How would the EEG classification system handle edge cases, such as noisy or artifact-ridden EEG data, when generating text? Should we develop a pre-processing pipeline that filters out such noise before feeding into the classification model, or could this be done dynamically? Regarding text to EEG generation, 1. How would we validate the synthetic EEG generated from text descriptions? Would it be sufficient to compare the frequency bands or power spectra of the generated signals to real EEG signals? Or should we evaluate the synthetic data's applicability in downstream tasks, like cognitive state classification? 2. What would the model need to account for in terms of the temporal dynamics of EEG signals when generating synthetic data from text? Should the model be designed to capture subtle time-dependent changes, e.g. phase shifts between brainwave frequencies, in addition to generating static waveforms? 3. Can existing generative models, e.g. GANs or VAEs, handle the complexity of EEG waveforms, which have both high temporal resolution and frequency-based information? Would we need to explore specialized architectures like time series GANs, or explore the use of transformers to generate synthetic time series data? 4. In terms of creating realistic synthetic EEG, how could we effectively map the textual descriptions of abstract concepts like focus or drowsiness to measurable EEG features? Would we need to define a fixed set of states and their corresponding EEG patterns, or could we allow the model to learn these mappings autonomously from the data? 5. How do we handle uncertainty in text descriptions that are vague or incomplete? For example, if the input description says the patient is resting but alert, how would we ensure that the generated EEG contains realistic elements of both states? Regarding the broader application of linking EEG with LLMs, 1. How would the system adapt to different types of EEG recording setups, e.g., high-density EEG with 128 channels versus low-density EEG with 14 channels? Would we need separate models for different channel configurations? Or could the system generalize across different setups? 2. In terms of clinical applicability, how would a system that converts EEG data to text and vice versa be used in practice? Could it assist clinicians in interpreting complex EEG data more quickly, or is the goal more focused on research and understanding brain states? 3. How would the performance of such a system be evaluated? Beyond traditional metrics like accuracy and precision, could we develop task-specific evaluations, such as how well the synthetic EEG generated from text resembles brain activity during particular cognitive or clinical tasks? 4. Could this system be extended to other types of brain imaging data, like fMRI or MEG? How well do the methods you're proposing scale to other neuroimaging modalities with different spatial and temporal characteristics? 5. From an ethical standpoint, how could this system be used responsibly in medical or research contexts? What safeguards would need to be in place to ensure that the synthetic EEG generated is not misinterpreted or misused, especially in clinical settings where diagnostic accuracy is critical? These questions are designed to critically examine the feasibility, accuracy, and potential applications of linking EEG data and language models. They focus on technical challenges, model reliability, and how the system would fit into real-world applications like research or clinical diagnostics. Here's a ranking of the questions by the level of difficulty, starting from the more straightforward to the more complex. I'll consider technical, methodological, and conceptual challenges when ranking them. Level 1, straightforward, foundational questions. 1. What specific types of EEG data are most suitable for generating meaningful text descriptions? This is relatively easy to approach because it mainly requires choosing the right dataset, e.g., task-based EEG, and literature review to inform the decision. 2. How would the system adapt to different types of EEG recording setups, e.g., high-density EEG with 128 channels versus low-density EEG with 14 channels? There are established pre-processing techniques and generalizable models that could handle different EEG setups. It's a practical engineering challenge, not an unsolved problem. 3. In terms of clinical applicability, how would a system that converts EEG data to text and vice versa be used in practice? While more conceptual, this is easy to address through interviews with clinicians or reviewing existing systems for interpreting biomedical data in clinical settings. 4. How would we validate the synthetic EEG generated from text descriptions? Validation methods, e.g., frequency band comparisons, are straightforward and based on existing standards in EEG analysis. It requires implementation, but is not conceptually difficult. Level 2, intermediate, technical, and practical challenges. 5. How do we handle uncertainty in text descriptions that are vague or incomplete? This requires more thoughtful design. Handling vague descriptions in a meaningful way, without oversimplifying, requires balancing creativity in the model and robustness in how the model interprets the input. 6. What would the model need to account for in terms of the temporal dynamics of EEG signals when generating synthetic data from text? Addressing temporal dynamics in EEG data requires designing or adopting models that handle sequential data effectively. This adds complexity, but there are existing models, like LSTM's RNNs, that could be adapted. Number 7. Have there been any studies that successfully combine machine learning with natural language processing to interpret biomedical signals in real time? Finding and reviewing relevant studies is relatively easy, but interpreting how applicable those methods are to your problem requires deeper investigation. 8. Can existing generative models, e.g. GANs or VAEs, handle the complexity of EEG waveforms? There is growing research on generative models for time series data, but EEG signals are particularly challenging. This is a technical difficulty, but it can be tackled by reviewing state-of-the-art time series GANs or VAEs and experimenting with different architectures. Given the limitations of current LLMs, how would we ensure that the generated text from EEG remains scientifically accurate and not overly generalized? This is tricky because while fine-tuning LLMs is doable, ensuring domain-specific accuracy, biomedical context, adds complexity. Pre-training or fine-tuning requires proper datasets and considerations of bias. Level 3, challenging, methodological, and conceptual. How would we handle the variability between individual EEG recordings when generating text? EEG signals can vary greatly between subjects, and generalizing across individuals without losing important information presents a major challenge. It requires advanced modeling techniques and potentially large datasets. 11. What would the model need to account for in terms of the temporal dynamics of EEG signals when generating synthetic data from text? Capturing temporal dynamics is non-trivial. While there are models designed for time series data, tuning them for EEG, where even small differences in waveforms can represent different cognitive states, requires careful design and testing. 12. How would the performance of such a system be evaluated? Beyond standard metrics, designing task-specific evaluations, e.g., how well synthetic EEG matches real EEG, adds complexity. This requires not only creativity in designing tests, but also domain-specific knowledge. 13. Could this system be extended to other types of brain imaging data, like fMRI or MEG? Scaling to other neuroimaging data like fMRI introduces more variables and challenges, including different spatial and temporal resolutions. The methodological shifts needed to handle different modalities make this more conceptually complex. Level 4, advanced, conceptually difficult, or unsolved challenges. 14. In terms of creating realistic synthetic EEG, how could we effectively map textual descriptions of abstract concepts like focus or drowsiness to measurable EEG features? This is very challenging because translating abstract cognitive states into EEG patterns is not a solved problem. It would require both domain knowledge and novel modeling techniques to establish meaningful mappings. 15. From an ethical standpoint, how could this system be used responsibly in medical or research contexts? Ethical considerations, especially around synthetic data, introduce complex interdisciplinary issues. Ensuring that synthetic EEG isn't misused requires a strong understanding of both the technical and ethical sides, including privacy, data validity, and the potential risks of synthetic data in diagnostics. 16. How do we ensure that the system remains scientifically accurate while generating understandable text for a non-expert audience? Balancing scientific accuracy and generating easy-to-understand explanations is a major challenge, especially in highly technical fields like EEG. It requires not only robust models, but a careful understanding of communication, knowledge representation, and domain-specific accuracy. Summary of rankings. Level 1. Foundational and practical questions around data handling, pre-processing, or general validation methods. Level 2. Intermediate technical and practical challenges around model design and applying existing solutions. Level 3. More complex, conceptual problems, particularly regarding generalization, performance evaluation, and extending the system to other types of data. Level 4. Advanced, often unsolved challenges in the field, particularly around abstract mappings, ethics, and bridging gaps between scientific accuracy and human interpretation. Here's a simplified summary of the rankings for a college student. Level 1, easier concepts, foundational questions. These questions are about the basic setup of your system. They deal with deciding what kind of EEG data to use and how to handle different setups, like EEG devices with fewer or more channels. You'll also explore how useful this system would be in a clinical setting and think about straightforward ways to validate if the synthetic EEG you create looks real. These questions focus on using existing tools and making practical decisions. Level 2. Moderate difficulty, technical and practical challenges. Here, you start thinking about the technical details, like how to deal with vague or incomplete text descriptions. You also need to consider the time-based nature of EEG signals and how text could be turned into realistic brainwave data. There's more focus on how to find useful studies and figure out which existing models could handle the complexity of EEG data. These questions require some understanding of machine learning and data modeling. Level 3, more complex, methodological and conceptual. These questions are harder because they involve tackling the variability in EEG signals from different people and figuring out how to fairly evaluate the system's performance. You also start exploring whether this method could be applied to other brain data, like fMRI, which would require some significant adjustments to the models. These are trickier because they involve both technical and conceptual challenges. Level 4. Very difficult or advanced challenges. At this level, you're dealing with some of the toughest questions. How do you translate abstract concepts like focus or relaxation into specific EEG patterns? How do you ensure that this system isn't misused in medical settings? There's also the challenge of making sure the text explanations are both scientifically accurate and easy for non experts to understand. These questions are complex because they involve ethical considerations and novel ideas in both neuroscience and machine learning. Summary of difficulty levels. Level 1, basic setup, practical decisions, easier to answer. Level 2, technical questions, requires some understanding of how EEG works and how models are designed. Level 3, more challenging questions about how to handle variability and evaluate performance. Level 4, very difficult, often involving abstract concepts, ethics, and unsolved challenges.